concept as we expect. So then we'll talk about matrices and various operations with matrices. Goes like that. So we'll sort of matrices in connection with the systems of linear equations. And then various operations with matrices. Their diagonalization, determinants of matrices, and so on. Etc. But it will be, most of that will be in the context of solutions of linear system of equations. And then there'll be a little bit of like sort of, yeah, then sort of little bit of algebra, algebraic structures like sort of well, vector spaces. Well, maybe we'll talk a little bit about groups, rings, fields, and also, well, and then we'll get to vector spaces. Sort of, it's the main object of linear algebra here. Well, we'll talk about classification and stuff like that. So then we'll do the eigenvalue equations. Eigenvectors, eigenfunctions, eigenvalues. And so on. And then depending on how much time we will have left, we'll have, we can either add some other topic, or we can talk about something that you want to add here, right? So I assume that some of you have taken some math classes before. So are you familiar with any of these concepts that I listed here, or are they all totally new for you? Or maybe you took some pre-calculus class or some kind of AP analog of classes in school or something like that. Like, okay, so we'll, if it's totally new to you, then this is okay. But I encourage some more participation from you. So like when I ask a question, like sort of, you can either reply in chat, or you can unmute yourself and then you can say it. Okay. So let's see if I had anything. Any questions about the syllabus? So syllabus, you have the PDF of the syllabus. Everything is in there. Okay. And as I said, this file, you'll get it after the class. Okay, so let's we can get going with the introduction then. So let's see what kind of geometric objects we know, right? So we know points, right? Which is basically it's like a point in space. It's then we have lines. I'm going to be sloppy at this moment, but then we'll try to find some logic behind it. It's a thing like that. And then we have planes. I want to illustrate. I want to talk about dimension first. What is a concept of dimension? So we say about lines that they are one-dimensional, right? So planes are typically two-dimensional. How about the point? How many dimensions are in the point? What would you think? What do you think? One? Well, a line is one-dimensional. So what do you think of a point? Well, if you go from planes which are two-dimensional to lines which are one-dimensional to points, I think what goes from 2, 1, what's next, right? It should be 0, right? It's something that doesn't have a size, right? Doesn't have a there's no dimension in there. It's really it's a point. It doesn't have any sort of. It's really like a point. Like it's basically nothing, right? Yet lines consist of points, right? You can put a point on a line. You can put 2 of them. You can put many, and same true for the plane. 0, yeah, that's right. Yeah, 0. Yeah. So the then, how do you think we would? How would you suggest to describe what is a dimension? So say you have a space, you have some, you have some object. How would you know how many dimensions are there? And then of course, like there's a sort of, if you go further to 3 dimensions, right? You have 3D objects, like, you know, like shaped like that, right? Some peanut, which is filled, or maybe a ball. So ball, it has to be filled with stuff, right? It's not just the surface of the ball, but actually that. And then the sort of we can call them solids. So yeah, solids are 3-dimensional, and again, they consist of points. Right? So what do you think distinguishes 0 from 1, from 2, from 3? How would we approach the notion of dimension? What do you think? Because the question might be a bit sort of, you may not understand why I'm asking this, but I can show you, like in a minute, I'll show you some particular examples of what will kind of question the idea of dimension. So, say when you have a line, right? So a line consists of many points, yeah, but good. But plane also consists of many points, many more points than in a line. We need some quantitative tool to describe lines and planes, and they should be different. So what does 1 refers to? Let me look at some examples that you should know, right? So let's try to draw some line in coordinate plane, right? So you have, so I'm assuming you're familiar with the Cartesian coordinate set, right? So we have X and Y. It's a plane of points, right? So we have every point on the plane has a unique address. It has a unique location, which is characterized by the pair of numbers, right? So let's call them A and B. It's an ordered pair where A and B. So these numbers, they represent the sort of the distances from the origin, right? So the plane has an origin, and this is point AB. So now let's draw the line over here, like this. Sorry. So there's a line that passes through the origin and that point AB. So can you describe me which equation we use to which equation describes this line? Y equals kx, where k is what? In terms of what I have written. Right, Sophie, I'm just going to mute you for a sec because unless you're saying something. Yeah. If you want to say, you're welcome. You're welcome to. What is k in terms of a and b here? It is. It's a proportionality line, a direct proportionality formula. So indeed, y is equal to some constant times x. Yeah, sure, but it's a constant. But what is this constant in terms of a and b? Yes, but slope. What is it? So I gave you a point. Say a is equal 1 and b is equal to 5. What is k then? So what was the question? I just missed it. So the question. So do you see the purple line that passes through point 0 and point with the coordinates a and b? The question is, what is the equation that defines the line? So the suggestion was that y is equal to some coefficient times x. What is the coefficient in terms of a and b? B over a, yeah, that's right. Of course, it's b over a, right? So it's the tangent of that angle, right? Which in this case is b over a. Okay, good. And yeah, of course, I'm sure we can find the equation for any line in coordinates plane. Now, so we say that the line is one-dimensional. So what does that what does it represent, right? So that so for every value of x here. So we pick a point on the x-axis, right? And then that uniquely fixes the point on the y-axis and the point on the line, right? And then if you take another point on the x-axis, it will give us a different point. So you can think of x here as a variable, as an argument that changes between minus infinity and plus infinity, right? So here, x can play a role of a parameter. It's a slightly different idea. So it's a parameter, and there's only one, right? So there's one parameter that describes you the position. It suffices. So because you know this coefficient b over a is fixed. So therefore, in order to find a point, any point on this line, it suffices to know just one value, x, right? So and that gives you the location of this point. That uniquely fixes the location of the point, right? Now that's what happens with the lines. Also, you can also write it slightly differently using parameters, right? So you can get some auxiliary parameter t. So say t is another parameter, and then you can say that y is equal to b times t, and x is equal to a times t, right? You can eliminate t from this equation, right? To if you say eliminate t from the second equation and solve it and put it in the first equation, you'll get y equals b over a as we had before. So but at any rate, so the fact that line is one-dimensional relies upon the fact that there's only one parameter that is used to describe it. Now let's talk about planes now. So to describe a plane, well, in a sense, you could think of this Cartesian xy plane as a plane, right? So it's a plane that has that has two parameters, a and b, right? So here, a changes between minus infinity and plus infinity, and same true with b, changes between minus infinity and plus infinity. So there are two parameters. So now here, both A and B, they are parameters. And of course, if you go to higher dimensions, right? So in 3 dimensions, you would need 3 parameters, right? So a 3-dimensional space, well, we'll talk about this in more detail a bit later in course. So we have three numbers, x, y, and z, and every point in space, at some point P, will have coordinates x, y, and z. It's an order triple. So again, here, this all these 3 guys are parameters. So in a sense, you can think of dimension. So dimension is the same as the number of parameters which describe the space. Let's put it loosely. Sort of, yeah, which let's put it like this, which describe every point of the space. Of the given space, right? Again, so we haven't. Yeah, sure. Yeah, I got it. Yes, you're right. So the I think the examples are self-explanatory. It's kind of more clear what is going on. But let me give you some just. Let's think about it for a second. I wanted to show you something different. So, in the sense that so it's not going to be, we're not going to talk about this too much during the class, but I just want to make sort of show you something that questions this definition of dimension and this new. So that phenomenon comes from what is known as fractals. Do you know what fractals are? You might have heard the word, right? So Iris says she didn't. How about Sophie? Okay, maybe once I'll start showing you pictures, you'll get some better ideas. So the, oh, interesting. Okay, so I'm going to show you some. Okay, so do you see these funny pictures like with the spikes and stuff? I just I changed the screen. I changed the screen sharing preferences. So this is something that is called Koch curve, right? It's over here, and it's a shape that can be obtained by iteratively applying certain operation, which I'll explain you in a second. So at first step, we have this thing. So if you use at step 0, you just have a piece of horizontal line, right? The horizontal segment. At step 1, you have this shape with a spike, so that the length of each of those segments is the same, right? It's like, so what you're doing, you break in at every step, you're breaking the interval at 3 equal parts, and then you draw horizontally first one, and then you make this spike in the second one, and then you continue. So at step 2, you get this shape, and at step 3, you have that shape. So it's and then you keep going, right? So for example, at step 6, you'll get that. So you see, it's getting denser and denser and denser. At step 8, you'll get, it takes a while for a computer to do. Well, it's basically, well, you're gonna have like this. So basically, see, it fattens out, right? So the it looks like as if it's fat, right? As if it's not just a single line, but some kind of smoothed out shape. And then you can ask yourself, what is the dimension of the thing, right? So how shall we understand the dimension? So the reason why it's interesting is because, well, so if we get back to the previous the examples that I just drew, right? So lines and planes, right? So what is a line, right? So line is something that has a length, right? So say it's a piece of segment, right? Just some segment AB. It has certain length, but its area is 0, right? So this line is infinitely thin from the point of view of 2 dimensions, right? So if you draw a line on a 2-dimensional plane, it looks as if it's infinitely thin. So if you do same way, if you have a plane, right? So if you live on a plane has, or like some planar object like a square, right? So a square has an area, right? And it has an area, but it has no volume. So if you put a square, if you draw a square on a piece of paper, so if you neglect the width of the sheet of paper, you should think of square as having 0 volume. Now, so what do you think will happen with the length of the segment? So say each of those segments has length 1, right, at every stage, right? So no, that's sorry. So that's coq 1. No, that's coq 2, and so on. So every little segment has length 1. So what will be the length of the whole shape as you change the number of iterations, as you increase it, as you send it to infinity? So what is the length of the coq curve? If it's just make a guess, it's more or less self-evident. So see, every time you make these things, like, so here, so the length is 1, 2, 3, 4, right? And here it's 1, 2, 3, 4, and then 3 more times. So it's 16. So here at stage 1, the length is 1. At stage 2, the length is 16. At stage 3, it will be, well, it will be some power of 4, right? So the length increases as you do more iterations. So if you do it infinitely many times, what the length will be? Yes, Sophie?
It's like give an equation for the increasing trend.
Yeah, like it increases, but just so see, every time we so if we go from iteration 1 to iteration 2 to iteration 3, we increase its length, right? So if you do it over and over and over again, in the limit, what the length will be?
In my guess, I think it's like 3 times 2, like.
Well,
for
that's like
second one.
If you go from one step to another, but if you so clearly you're increasing it every time, right? So you go from 4 to 16, then to probably 64, right? It should be power of 4. So if you do it over and over and over again, it will grow indefinitely, right? So it will go to infinity, right?
Yeah.
If you agree with the procedure. So length is infinite, right? But somehow we managed to, so in that square, length is infinite, but what we can do a tricky thing. So we kind of, every time we go from each step to the next one, we kind of increase the length, but then we can also gonna squeeze the shape a little bit. So let me, so let's say it's drawn in the same kind of shape. So, excuse me, I'll explain in a second what I mean, right? So okay, second two, now I think it's okay, right? So there are 3 steps. So now see that, let's say now I'm gonna fix the scale. I'm gonna fix the size. So think of it as like a box, right? This orange box. And then at step 1, I have this shape. At step 2, I have this shape. At step 3, I have that shape, and so on, right? So like every time I do another step, I stay within the same box, right? So I don't want to increase the size anymore. So, but you can also think about this way, that you actually do increase the length, but then you scale it back, right? So like this fragment, right? So this whole curve on step 1, it's only a part of the curve at step 2, right? It's this kind of thing over here on the left, and also here, and also here, and also and also there, right? So basically, if you zoom in, or like zoom out by a factor of 3, right? Then you'll get from step 1 to step 2, and then from step 2 to step 3, right? Is it clear? So like the length changes by a factor of 3, like the length scale, because basically every time you go from here to here, I explained that. But now let's calculate by how much the the number of segments change, right? So you should think of this as, so like the so length changes by a factor of 3, but by how much does number of segments change? By which factor? We talked about, right? So if this is 4, this is already 16. $72, I think 72 is from what? So okay, are you talking about step 3 now, or you just counted them? Or no, like it's like, okay, maybe, let me try to rephrase that. So the so here we had, right, so here we had 4 segments in step 1, and in step 2 we have 16, right? So number of segments change by square. Yes, that's right. But no, or like, yeah, so it's 4 to that power, indeed. So here at step 1 we had 4 segments. I apologize, my neighbor is having a party. I'm gonna close to here. So, and then at stage 2 we had 16, which is power of 4. That's right. So it's 4 squared. So it's here, it's 4 to the 1, it's 4 to the 2, and so on. And here it's at the next step is 4 to the 3. Right. So then indeed goes in power of 4. So and we just agreed that the length scale changes by a factor of 3. So the number of so now we can think of segment as being made of some thin piece of wire, right? And what you're doing is you're measuring the mass, like the weight of that piece of wire. So, and then you can say, okay, by how much did the length, like the number of the segments, changed as we increase the scale by, say, a factor of 3, right? So in other words, so we had say 4. Well, basically, this is the answer here. So what I'm leading to is the following: is that you can define a dimension in the following way, that it's the number to which you need to exponentiate the scale factor, right, to get the weight factor, right? So let me give you an example of why this can be the case. So I'm going to stop sharing. I'm going to draw it on a different, draw it on the on a tablet here. So how do we know that the square is 2-dimensional? Share screen. Yeah, there we go. So how do you know, say, that the square is 2-dimensional? So say the length of the side of the square is 1, right? And then on the next on the next stage, we increased it by a factor of we doubled it, right? So right? So it was 1. Sorry, I'm gonna close the window here. Okay, so maybe let's do it first. So first we have a square of scale 1 of the side 1, excuse me, and then on the next slide we have it of size 2. Every time we're going to double it, right? And then and the next step we have size 4. Right, so it's just 2 squared, and so on, right? So now between steps 1 and 2, we can calculate by how much the square became heavier, right? So if you think about physics terms, so if the size of the square increased by a factor of 2, the mass of the square, right, increased by a factor of 4, right? So therefore we can say that 4 equals 2 to power 2, right? And then we say that 2 is the dimension, right? So you can think of a dimension as the exponent which sort of governs this equation. So by how much the weight of the square changed as opposed to its length, right? If you go to 3 dimensions, you can do this. You can do the same exercise. So if you have a little cube of unit size, so little cube with a unit length 1, and then you double the side, right? So here we have 2, right? And then of course you know that you can cut the cube into how many small cubes of 1 by 1. There will be 8 cubes, right? So there will be 8 cubes. So here you can say that's right. So you're saying 2 to the power 3 because we already know that 8 is equal to 2 to the power 3. And here we say that 3 is the dimension. Okay. So that's easy. It's even sort of plainly evident. However, if you want to apply this logic to fractals, then you get something interesting, right? So let's get back to Mathematica. So here, the scale, the length scale, have changed by a factor of 3, right? But the weight, sort of the mass, have changed by a factor of 4. So the dimension, whatever it is, should be thing that should be the number that solves this equation. 4 equals 3 to the power d. Okay, well, the solution of this equation is this, right? It's log 3 divided by log 4, and if you evaluate this numerically, you'll get 1.2662 or something like that. So in a sense, this shape is called a fractal. It's one of the example of fractals out of many, and in a sense, fractal the name itself comes from the fact that the dimension is not integer, so that they have fractional dimension. Okay, so I'll give you links to on basically there's a Wikipedia page and there's a lot of sources on the internet about fractals, but it's good because you should think of it as something that has, it's not like it's something out of ordinary. Right? It does not have an integer dimension. So in a sense, you can define fractal like that. Was this clear? Was the explanation about log 3 or log 4 or log 3? Did you get that? Okay, so there's still questions, but yeah, so you can define dimension as something which is sort of, you can define it like that. It's something that is obtained by observing how the shape scales. in a sense, sort of what I told you before, if you draw a curve at higher numbers, sort of for 7, it does look a bit thick, right? It's not, it's something not one-dimensional. So its length is infinity because I always increase the number of spikes, and its area is 0. So neither length nor area are good quantities to describe to describe that thing. Okay. So it might be a bit. So if it's not quite clear, let's do another example. It's called piano curve. So again, it's a self-similar shape that looks like this. So at stage 1, you have this kind of number 5 kind of shape. At stage 2, you get, well, something more complicated. At stage 3, you get something more complicated still. And basically it keeps going, right? It's kind of, so it's a certain pattern that kind of self-replicates itself, and then you draw this you draw this kind of number 5, and it's mirror reflection all over the place. And then you can do the same exercise. So you can calculate its dimension. It's also called fractal dimension. So we can try to calculate a fractal dimension here. So say here at step 1 we have how many segments we need to. So here the vertical segment here is twice shorter than the horizontal one. So we should count them with so the horizontal one is say 2 in some units, and vertical is 1. So how many segments do we have here in figure 5? 10, 8, that's right. Yeah, so step 1, we have 8 segments. Let's do step 2. How many you have at step 2? I hope you're not gonna, you can come up with some smart algorithm to count them. Basically, you should think like of this kind of prong as 1, right? So basically, there's a 5, then there's a mirror 5, and so on. So step 2, and then also I'm going to give you the next one as step 3. I could actually maybe pull up some more, while counting, some more convenient picture. How many? Sorry. So maybe I can show you first 3 steps at once. Just I'm going to show you the PDF here. Do you see the PDF, right? So so these are the piano curve for 3 steps. So let's count two things, right? So number of segments in steps. Well, 1 we already have, it's 8. Well, 1, 2, and 3. And then we change the length of the side of each square in the same unit. So step 1, length is equal to 2. At step 2, length is equal to what? And same with step 3. Is the question, are the questions clear or not quite? Just count the length in units of those. So like, yes, we have 2, that's 1, 2, 8. So right, it's 8. Right, good. So it's the question, it's the answer about the length, right, Sophie? That's right. So step 2, the length. So length at step 2 is 8. Length of 2 is equal to 8. So yeah, those length, they're easier to count, right? They are 2, 8. How about step 3? So count a number of, count the length, count the number of segments. But I hope you're not just gonna count them, you just need to find the formula for it. And you'll see there'll be fun surprise after that. I'll be back in a minute, yeah, so you can count now. Okay, I'm back. So I see that we counted the, where's the PDF? There you go. So 26, right? So I think 26 is the right answer. So 26 is the number of segments for step 2. Is that right, Sophie? So number of segments goes like this. It goes 8, then 26. So we're trying to find the pattern here. And then you'll see in a second why we're doing that. Can we quickly count number of segments in step 3? You'll see that after we have completed it, there will be a surprise. "26 is the length of the third picture." Oh, okay. So I'm sorry. Okay, I think I misheard what I said. Yeah, it should be 26, right? Was it? So it's oh, yeah, sorry, that's right. Yeah, sorry. Okay, so yeah, I'll ignore my previous comment, right? So it's a length, right? So lengths they go like 2. Good. So thank you. Yeah. So 2, 8, and then 20, 26. So let's check, right? So it's 2 here. Right. So basically, it's we can put 3 shapes like this, right? So we have we can embed 3 shapes from step 2 into the into step 3, right? So there's kind of 1, 2, and 3. So each of them has 8. So it's 8 times 4, 8 times 3 plus 2. Okay, that's right. So these are the length, and now let's count the number of segments. And then we need to find patterns in these groups. Number of segments goes as 8. So I think the fastest way would be to count how many number of files we have at step 2, and then count the number of segments that connect them. All right, so how many you have? 1, 2, 3, and then there are 3 more, right? So there's 4, 5, 6, 7, 8, 9, and then you need to find the number of connectors, right? There's 1 here, 1 there. So there are 2 in the first row, 2 in the second row. Right, so it's what, 3 times. So it's what, 3 times, excuse me, not 3, 9, right? So 9 times 8, and then plus how many? Plus 1, 2, 3, 4, 5, 6, and then 7 and 8, right? So there are 2 vertical and then 6 horizontal. So that makes us what? It makes us 9 times 8 plus 8. How much is that? That's 80, right? Okay, and then let's finally find the number of segments in the third picture. Again, you can count in the same way. You can see that you can count how many times the shape from step 2 fits inside the picture, right? And then you need to count how many more segments we need to add. All right, so we have what, nine again. So like every sort of step 2 fits inside step 3 9 times, right? There's in each row we can put 3 blocks from step 2, and now so it will be 9 times 80, right? And then we need to count the number of sort of lines that connect them, right? So, and again, it would be line here, 1, 2. So in every row, in every horizontal row, there will be 2, and there will be two vertical ones. So there's 1, 2 here, and then 3. Sorry, 3 and 4. 976. How do you get to 976? So it will be what, 9 times 80 plus something, right? So 9 times 80, it's 720. 720. So it will be 720 plus plus the number of connections between them, right? So it will be sort of every horizontal row has basically it almost goes as 9 to some power, right? But there are some corrections, right? There's this small thing here. That's 1, 2, 3, 4, 5, 6, and then there are 2 vertical ones, right? So it will be 928 plus 8 is equal to 728, right? Was it clear how I counted? Good. So now we have the pattern 8, 80, 728. Can you find the pattern? Can you write it as can you find it using some power and then maybe minus something? So we have 2 patterns: 8, 80, 20, 8, 80, 728, and 2, 8, and 26. Sixteen times 80 plus 26. What is that? It's the answer for what? The next. Oh yeah, that's right. Yeah. Well, no, sorry, no, not 6. No, I don't think it's quite right. So on the next step, actually, I have a picture of the next step. So let me show you the next step. So I did the picture for the next step as well. So it will be here. So it will be 65, 65, 60. So the way you can count it is by so again, like step 3 will be here is written in black, right? And then again, you can see that it fits the black square in step 3 fits 9 times, right? In the blue square at step 4, right? So you can put it 3 times horizontally and 3 times vertically, but it doesn't fit. So the formula for step 4 will be again, so we need to take 9 times the number on the previous one, 728, and then again plus 8. So every time you multiply by 9 and add 8, right? So you can have, so you have 8 is just nothing. We don't. It's like 8 is equal to, well, it's just 8 itself, right? And then we have a 80, which is 9 times 8 plus 8. That's 80. And then we have 728, which is 9 times 80 plus 8. But can you do even better? Can we write this sequence as a power of 3? Actually, a power of 9, right? So 8, we can write what is 9 minus 1, right? So how about 80? Is there a simple formula that has power of 9 with it? Yeah, sure. Yeah, 80 is 9 squared minus 1. And how about 728? Yep, absolutely. So we got the pattern. So it's 9 to an integer. It's 9 to the n minus 1. That's number of segments. So how about the pattern for the length? So remember the answers were 2, 8, 26. Can you get a simple formula that describes this sequence? You may try a different base, some different number to power n. Yep, absolutely. Good job. Good job. Right. So 8 is indeed 9 minus 1, and 27 is 26 is 27 minus 1, which is 3 cubed. So length goes as 3 to the power n minus 1. And number of segments goes as 9 to the power n minus 1. Now, what do you think will happen? Well, so clearly when n is a large number, like large enough, even say 3 or 4, you can ignore this minus 1, right? So therefore, number of segments goes 9 to the power to the integer, and the length goes as 3 to the integer. So what do you think that is the dimension of this fractal, of the Peano curve, based on what we discussed so far? So remember, dimension is, we define the fractal dimension as the exponent to which we need to put, which solves the equation that so like essentially the mass of the segment of the fractal should go as length factor to that power. If you ignore this minus 1, what will happen? I'll get back to Mathematica. So remember that 9 is 3 squared, right? So then what will be the proper exponential? Yeah, what is the fractal dimension of that thing? Yeah. So, so remember with the cut curve, it was log 4 of log 3. So what is log 9 divided by log 3? What is that equal to? So here log is the natural log. Two, yeah, exactly. So this fractal has dimension 2, which is a bit surprising. So in a sense, let me show you how this works. So this is piano curve at stage 2. This is piano curve at stage 3. That is a piano curve at stage 4. Okay, so it's becoming denser and denser. Stage 5, stage 6. Well, what do you see at stage 6? How would you describe that shape? Is it, well, I mean, you can kind of, if you zoom in, it doesn't cover the full square. There's some gaps, but these gaps, they become smaller and smaller as you kind of contract it down. So for example, at stage 7, it will be again the black square, right? So what this curve does, it covers every point, it passes through every point of the square at least once. So in fact, it will pass through each point many times, through some of the points infinitely many times. But the bottom line is that it's a curve which sort of we used to count as something one-dimensional, right? But now it covers completely covers the square. So it's something, this is truly extraordinary. Like it's kind of, it defies our understanding of what the dimension is and how to understand that. So in a sense, this is a curve, like it's a bunch of segments, bunch of sort of piecewise smooth collection of segments, and yet it covers completely the square. Okay, so in our course, of course, we're not going to do this, but it just shows you that even the notion of the dimension is very tricky. It sort of, if you use the dimension as sort of if you think of a dimension as the number of parameters that describe it, then here the number of parameters is 1, right? And yet there is, you can think of it as having an area, right? So it gets it covered. Okay, any questions? Okay, good. So I'm going to go back to the screen share. So I think we should stop at about 10 minutes before the end of the hour. So like folks with the next class will have enough time to rejoin. Okay. Yeah, so the dimensions are tricky. Okay. And now let's talk about the definition of the dimension, sort of, which we will use in this class. Namely, we should think of the number of parameters that describe the set of points. So what we're going to do, well, today and tomorrow, we'll look at a system of equations. Systems of equations. Describing well, various sets of points. So example would be, so you have some function, and then it depends on some number of variables, say x1 and so on through xn. And in fact, there can be many functions. There can be f1 is equal to 0, then f2 of x1 through xn is equal to 0, and then so on. Say fm, a different letter, x1 through xn, nic, right, is equal to 0. So yeah, so there is a set of equations like that. So in principle, this f1 through fm can be any function, right? So so f1 through fn, any functions, exponentials, for example, or logarithms, or polynomials. So in mathematics, there are two big branches of science which study very particular types of equations. So you probably heard of algebraic geometry. So it studies solutions of these sets of equations when these functions are polynomial. f1 through fn are polynomial. They're polynomial in those variables, right? So for example, f1 can be x1 squared plus x1 x2 x3 plus x3 to the power 7. All right, so that's a perfect example of a polynomial. So this is a more complicated story, and what we're going to do, we will talk about linear functions. So a very important class of examples is linear functions. Excuse me. So linear functions appear in linear algebra. Yeah. So in linear algebra, which is what we're going to talk about, these functions are linear. So they are linear in x1 through xn. And what it means in particular is that, well, so linear means that, say, a function is linear if you can say that, yes, let's say f1 through x1 through xn is equal to a1 x1 plus a2 x2 plus etc. plus an xn. And there might be a constant, right? And maybe plus some b, right? So these are, so this is called we multiply with these coefficients. A1, A2, etc., an, and b are either real numbers or complex numbers. Are you familiar with complex numbers? We're not going to need them too much, but just in case. So for example, yes or no? A little bit, yeah, okay. Sorry. Yeah, so it just sometimes when you know, for example, the necessity of introducing complex numbers appears when you say want to solve quadratic equation with negative discriminant, right? That's one thing where I is, but in linear algebra problems, when we'll solve some, you know, find solutions of some eigenvalue equations, we may also need some complex numbers. So, no, so real numbers we can denote them with R, complex with C. And then here, see, like there's also the index here is F1. So in particular, they should have this set of numbers for every function, right? So let me maybe erase it here. So that's F. And now if you have system of equations like that, then you write something like F1 of x1 through xn is equal to A11 x1 plus A12 x2 plus etc. plus A1n xn plus B1, right? Then F2 of x1 xn will be equal to A21, this is 1, A21 x1 plus F22 x2 plus etc. plus A 2n xn plus B2 and so on and so forth. And then the last one, the Fm x1 xn, Am1 x1. To understand the notation, basically the first index, so these coefficients, we have the whole table worth of coefficients, which have the first index corresponds to the labels the function, and then the second corresponds to the coefficient to which monomial, sort of to which variable it is attached. So, and then am2 x2 plus etc. plus a mn xn plus bm. And of course, later we'll use matrices to write this all down. So we can define a matrix A, which will be a rectangular matrix of size m by n. So it will have n rows, the same number as number of functions, and m columns. Right, so we have A11, A12, and so on, A1n, A21, A22, A2n, and so on, A1, AM2, AMN. So, and then we'll use matrix calculus to sort of operations with matrices to solve this systems of linear equations. So let's see what's the geometry behind it, right? So let's look at let's basically our first task is to understand what does it mean to solve the system of equations like that, right? So so system of equations to be that this set of that this is all equal to 0, right? So say this is equal to 0, this is equal to 0, etc. This is equal to 0. So the question is, what is the geometric meaning of the set of solutions of linear equations? right? In a sense, that's what that's all what a linear algebra is about. Okay. So let's take an example. Are there any questions? Yeah, please, if you think I'm going too fast or too slow, or if anything's unclear, just let me know. So take an example. So 5x1 plus 6x2 is equal to 1. And then x1 minus x2 is equal to 3. And so what is the set of solution of this system of equations? Then let's solve it for x1 and x2. Yeah, so basically I is saying it's 19/11. So let's check. So let's say 19/11 minus 14/11 is equal to so that's 33. 11s, that's 3, and then so it's 5 times 19 minus 6 times 14. I think it looks correct. Yeah, sort of basically right. So basically you plug it in there, and then you get so let's write down. So yes, x1 is equal to, we're going to eliminate it from second row. So x1 is equal to x2 plus 3, and then plug it in the first equation. So 5x2 plus 15 plus 6x2 is equal to 1. So it's 11x2 is equal to negative 14. Yeah, that is correct. So x2 is equal to minus 11 14/11, and then x1 is equal to 19/11. Right. So the set of solutions is just one point, right? Which you can write sort of join the coordinate system, right? It's somewhere in the fourth quadrant, right? Somewhere here. Okay. Good. So that's the first example. For example, a set of solutions can be one point. Now let's give you another example. Say 2x1 plus 4x2 equals 5, and 4x1 plus 8x2 equals 10. These are two equations. What's the set of solutions for those? What do you think? Infinite solutions. Yeah. So Indeed. So the reason why the case is because, well, you can, if you try to eliminate say x1 or x2 and then put it back, you'll see that the equality is satisfied for every value of x1 and x2. But there is this math. Yeah. So here, right, so we'll just go here. There was one solution, right? Here we have two solutions. Here we have infinitely many solutions. And sort of the way to see it, so we can just say, okay, let's multiply the left and right hand side of the second equation by 2. So we multiply left hand side by 2 and sorry, divide, excuse me. Or we can do, let's multiply by 2 the first equation. So it would be simpler. So 2 times the left hand side equals 2 times the right hand side. And you can see that you get exactly the second equation. So in a sense, the second equation does not give you any new information for the system. So you can just describe it by one equation. And of course, you can draw it as a line, right? So in the coordinate system, so it's 2x1 plus 4x2 is equal to 5, right? So how will this line go? Right, so it has slope -2, right? And then when x1 is equal to 0, x2 is equal to 5/4, right? And then when x2 is equal to 0, it's equal to 5 seconds. So it's a bit, it's like, the slope is 1/2, excuse me, so like this, right? And the line goes like that. So every point on this line is a solution. Okay, and here, by the way, in the first example, so that point appeared as the intersection of two lines, right? So the first line, so if you draw it, it's x1 as x2 equals 1. So it's yeah. So here when x1 is equal to 0, it's equal to 6, right? When x2 is equal to 0, it's equal to 1/5. Well, I'm just gonna redraw it. So it's the line that goes like that. That's the first equation, and second equation, it's like x2 is equal to x1 minus 3, right? So it's to go like that. They'll intersect at a point. So the purple is the first, the green is the second. So these two lines intersect at a point, and then finally we can get an example. That probably will be one of the last thing today. Let's take, we have x1 minus 2x2 equals -1, and then minus x1 plus 2x2 is equal to 3. What's the set of solutions here? No solution. Yep, that's right. So you can either you can see it by itself, but so yeah. So or sort of you can say set theoretically it's an empty set. The set of solutions is empty set. Empty set or no solutions. So what happens geometrically? How will these two lines look like if you draw the if you plot them? How they describe so each of these equations is a line, right? What's lines are do not intersect, or they are parallel. That's right. So here, if you draw them, one will go like that. So it's a line with slope 1/2, right? And then the other will go like that, right? So this it's a pair of parallel lines. And you can imagine that that's all that there can be, right? So not only when you have two equations and two variables, but in general, the set of solutions of any linear system can be of any of these three types, right? So it's either it has one solution, or it has infinitely many solutions, or it has none, right? So that this is the something that will appear over and over and over again during this course. Okay, good. I think the time is, so yeah, we need some time for you to have a break and to prepare for the next course. I'm reading the next class right now, so at well, 10 p.m. my time. So are there any questions about anything? So the homework is out. You can read the book, right? I forgot to mention the book, right? So this Lay and McDonald. I hope you have it. If not, then let me know. I can send you the PDF. And yeah, so we'll continue tomorrow with matrix notation and elimination procedure and stuff. Okay. Great. See you tomorrow then. It was nice to meet you. Bye.